Hello everyone, I'm Dan Fullerton, and today we're going to take a look at the 2018 AP Physics C Mechanics free response questions. Now, just a quick disclaimer as I'm doing these, they haven't released the scoring guides yet, so I've just done a quick run at these trying to get them up quickly. And chances are I probably miss a couple points or two by going too fast or missing minor details. So this may not be perfect solutions, but hopefully it will at least give you an idea of how to go about attacking the problems. So let's dive in right here with number 1. We have our sphere that's being dropped by an electromagnet onto a pad sitting on a table from some distance h. It says, while taking the first data point, the student notices the electromagnet releases the sphere after the timer begins. Would the value of g calculated be greater, less than, or equal to the actual value? Well, the way I would go about doing this is recognize that what we're really doing is we're verifying our kinematic equation for constant acceleration. D is 1/2 at squared plus VIT, where our initial velocity is going to be 0, so that whole term goes away. Our distance it falls is h, so h is 1/2 at squared, and what we're solving for is actually the acceleration due to gravity, the acceleration a, so that's 2h over t squared. Now, looking at that, our t is going to be too large compared to the actual time. And since that's in the denominator, I would state that our calculated value of g is going to be too small. So this is going to be less than for 1a. And I think we just justified our answer. All right, now the electromagnet is replaced and fixed, so it works when the sphere is released. The student varies the distance h and records some data. All right, let's take a look there. There's our table of data. Indicate which quantities should be graphed to yield a straight line whose slope could be used to calculate the numerical value for g. There are a couple ways you could do this, but to my mind, we just said that the acceleration, which should be g, is 2h over t squared. So our slope of our graph, if we want it to be g, or the acceleration a, should be 2h over t squared, and that's going to be our rise over run. So our rise, our y-axis, I would have our y-axis, our vertical. Let's graph 2h. And our horizontal, our run, let's graph the square of our time, or they use delta t here, delta t squared. So if we made that graph, the slope should be our acceleration, which should be g. So then it says, use the remaining rows on the table to record our quantities and label each row in units. So we would have our 2h, which would be in meters, and delta t squared, which will work out to be in seconds squared. Then I just go through with my calculator and fill in these different points. Get something close to 0.2, 0.4, 1.2, 1.6, and 2 meters for 2h. And 0.011, 0.045, 0.117, 0.161, and 0.203 for delta t squared. So I think that covers us for 1b. Taking a look now for 1c, it wants us to go and plot those data points. All right, and I won't make you watch as I plot all of these, but very quickly I have something that looked kind of like this. And I'm going pretty quick here, so I might not be exactly on where I have my points. But something kind of close to this, where we have 2h in meters over here, and we have, delta t squared in seconds squared down here. And our scales, I used 2, 1.6, 1.2, 0.8, 0.4, 0, and our times 0.05, 0.1, 0.15, 0.2, 0.25 in seconds squared. So that was my graph. Then we go through, draw our best fit line. So I recall our best fit line here did something kind of like that. And using that straight line now, calculate an experimental value for g. So our experimental value for g is going to be the slope of this, which is rise over run, or y2 minus y1 over x2 minus x1. And anytime you do this, I recommend you go and you circle the points on the graph. You are not specifically using data points. So looking at points on the graph depends on how you drew it. Try and pick some things close to the end that are pretty easy to grab values for. They don't have to be the endpoints. Look for where you have your line crossing the graph. But when you do that, you should come up with something around 10 meters per second squared is what I calculated, just on a quick look on that graph. And that should make sense. You should get something pretty close to the 9.81 as the accepted value. All right, so I think that covers us for D. Now it says another student fits the data in the table to a quadratic equation. Perfectly reasonable way to go about doing this. And they come up with the equation y is at squared plus bt plus c. And it tells you what a, b, and c are those constant. Vertically down is the positive direction. So then, using the student's equation above, do the following. Derive an expression for the velocity of the sphere as a function of time. All right, to do that, well, it's giving us position. Velocity is the derivative of the position with respect to time. So that's just going to be 2at plus b, which will be 2 times our 5.75 meters per second squared times our time plus b, where b is negative 0.524 meters per second. So work that out. I come up with about 11.5. So that's going to be meters per second squared times t minus 0.524 meters per second. So I think that gets us in pretty good shape for E1. Now, E2, calculate the new experimental value for G. All right, again, you can do this several ways, but I would probably go with acceleration being the second derivative of position with respect to time, or the first derivative of velocity with respect to time. Looking at that, that's just going to be 11.5 meters per second squared. All right. Part 3, using 9.81 as the accepted value, find the percent error. All right, hopefully you have lots of practice in doing that from various labs. Percent error is going to be the absolute value of your answer minus the accepted answer all over the accepted times 100%, which for me came out to about 17.3%. And part 4, assuming the sphere is at a height of 1.4 meters at t equals 0, find the velocity just before it strikes the pad. All right, so we know y equals at squared plus bt plus c, and our distance is going to be 1.4, so I'm going to plug in our 1.4 meters for our y equals a 5.75 t squared minus 0.524 t plus 0.08. And I'm going to solve that for t. And you could use the quadratic equation or another method. The nice thing is on this exam you can use calculators. So I am going to use my calculator, plug it into the solver, and come up very quickly with a nice value for t of about 0.527 seconds. So it's in the air 0.527 seconds when it's gone 1.4 meters. Now all I have to do is plug that into the equation I came up with earlier for velocity right up there. So our velocity is 11.5 meters per second squared times t, 0.527 seconds, minus 0.524. Come up with the value of about 5.54 meters per second. And I think that covers you now for question 1. Question 2. Now we have our collision with the force sensor. Two carts on a horizontal level track with no friction. Cart 1 is a sensor that measures the force on it. Looks like they're going to hit each other. They model the data that's given from something like a Vernier Logger Pro or Pasco tool. And you see the force versus time graph there. And the quadratic fit says that force equals 3,200 newtons per second squared t squared minus 500 newtons per second t. Part A, using integral calculus, find the total impulse delivered to cart 1 during the collision. All right, the impulse is going to be the integral from t equals 0 to our final value of t of our force over that time. So, first thing I need to do is I need to figure out what my maximum t value is going to be there. So what I'm going to do is just very quickly is I'm going to take our equation 3,200t squared minus 500t and find the zeros of it. Obviously, if t is 0, our force is 0, so that's where we're going to start. But our second 0 is going to happen when 0 is 3,200t squared minus 500t. Divide a t out, 0 equals 3,200t minus 500. Or solving then for t, I come up with about 0.15625 seconds. So I'm going to make my maximum t 0.15625 seconds as my limits of integration. One way to do this. All right, so that's going to be the integral from 0 to 0.15625 seconds of 3,200t squared minus 500t with respect to t. All right, that implies that our impulse is going to be 3,200 t cubed over 3 minus 500 t squared over 2, all evaluated from 0 to 0.15625 seconds. Plug those in, and I come up with a value of about negative 2.03 newton seconds, or negative 2.03 kilogram meters per second. Different ways of stating the same value. So there, I think we've found part A, our impulse. All right, now part B is going to have us calculate the speed of cart 1 after the collision. Okay, let's give ourselves a little more room here. Calculate the speed of cart 1 after the collision. Well, I would note there that the impulse is the change in momentum, which is the final momentum minus the initial momentum. Therefore, the impulse we found, negative 2.03 newton seconds, must equal our final momentum minus the initial momentum, which would be 3 meters per second times half a kilogram. So solving this for our final momentum, I come up with, let's see, negative 0.53 newton seconds. But it doesn't want final momentum, it wants final velocity. So recognize the final momentum is mass times final velocity is negative 0.53 newton seconds. And we know that mass, so final velocity, is going to be negative 0.53 newton seconds over our mass, 0.5 kilograms, which works out to be about negative 1.06 meters per second. The negative tells us it's moving to the left with a speed of 1.06 meters per second. Okay, I think that covers us for part B. All right, part C, we're going to find the speed of cart 2 after the collision. Let's give ourselves some more room again. Part C, impulse is change in momentum again, which is momentum final minus momentum initial. Therefore, momentum final will be the impulse plus our initial momentum. But in this case, its initial momentum is 0. Therefore, final momentum is just going to be that impulse. Final momentum is 2.03 newton seconds. And here we're using Newton's third law, recognizing the force one way is equal to the force in the opposite direction, and that conservation of impulse. Conservation of momentum, excuse me. Therefore, P final is 2.03 newton seconds. Mass times velocity final must be 2.03 newton seconds, or velocity final is going to be our 2.03 Newton seconds divided by our mass, which for our second cart is 1.05 kilograms, giving us a velocity of 1.93 meters per second. And for C2, show that the collision between the two carts is elastic. Well, in an elastic collision, kinetic energy is conserved. Therefore, for part 2C2, kinetic energy initial must equal kinetic energy final. All right, all we have to do then is show the initial kinetic energy, which is 1/2 mv initial squared, must be equal to 1/2 mass 1 v1 final squared plus 1/2 mass 2 v2 final squared. Oh, don't quite know what I'm doing here. 1/2 m v initial squared. It's not the whole thing squared. Writing a little bit too quickly. There, that's better. Now we just have to plug in our different values here, which implies then that 1/2, our initial mass, 0.5, times our velocity, 3 squared equals 1/2, times mass 1, 0.5, times its final velocity, 1.06 squared, plus 1/2 times our mass, 1.05, times its final velocity squared. So those have to be equal. I go through, I do the left-hand side, I come up with 2.25 joules. I do the right-hand side, I came up with 2.24 joules. Slightly different, but remember we are also having some rounding errors. I am only sticking with about 3 significant figures, so we'll say that that's approximately equal. I'm sure if I did more figures that would be exactly equal. We've shown that the kinetic energy before is equal to the kinetic energy after. Therefore, the collision is elastic. All right, moving on to part D. Calculate the speed of the center of mass of the two-cart spring system. All right, the speed of the center of mass of the two-cart spring system. Well, we know that we have 1.5 kilogram meters per second. Our initial momentum has to be equal to the velocity of the center of the mass times our final total mass, 1.55 kilograms, by conservation of momentum. Therefore, velocity of our center of mass is about 0.968 meters per second. In the absence of outside forces, that's going to remain constant. All right, and D2, find the maximum elastic potential energy stored in the spring. The way I do that is from a conservation of energy perspective. The kinetic energy of the center of mass of our system is 1/2 times our mass times the velocity of our center of mass squared, which is 1/2 times 1.55 kilograms times 0.968 meters per second squared, or about 0.726 joules. Now we know we initially started with 2.25 joules, all kinetic energy. Conservation of energy says that we didn't create or destroy energy. Therefore, the maximum potential energy in the spring will be our initial total energy, 2.25 joules, minus what we have in kinetic energy, 0.726 joules, which leaves us with about 1.52 joules as the maximum we can store in that spring. And I think that covers us pretty well for number 2. Moving on to number 3, our rotation problem. We have a triangular rod with some length L, mass m, and a non-uniform linear mass density. Find the rotational inertia of the rod about its left end. All right, well, the way I would start that is recognize that the moment of inertia is the integral of r squared dm, where we know our linear mass density, which is mass per length. In our case, we are not going to have a constant. Instead, what we're going to have is a differential of mass, 2m over L squared times x. And we'll also have a dx in there, because what we're going to do is, as we go through, we're going to break this up into little chunks of with dx. And in each little chunk, we have a differential of mass, 2m over L squared times x. So our integral becomes the integral from x equals 0 to x equals some final value L of r squared, in our case, x squared, times our dm, which will be 2m over L squared x dx. Moment of inertia is the integral from x equals 0 to L of 2m over L squared, a constant, times x cubed dx. We can pull the constant out of the integral sign, so 2m over L squared, integral from x equals 0 to L of x cubed dx, which will be 2m over L squared, x to the 4th over 4, evaluated from 0 to L, which becomes 2m over L squared. We'll have L to the 4th over 4 minus 0, which works out to be, looks like ml squared over 2 for each of those little triangular buggers. All right, so that's the moment of inertia of the rod. And yes, it says show that its value is ml squared over 2. Looks like that came out okay, so we probably did it correctly. Now, it looks like for part B, the thin hoop shown in figure 1 has mass m, radius L, and moment of inertia ml squared about its center, and we're going to put 3 hoops in there, 3 rods in there too. So find the total rotational inertia of the system about the center of the hoop. Derive an expression, answer in terms of ml and physical constants. Well, the total is going to be just the sum of the 3 rods, so we'll have 3 ml squared over 2, plus we have ml squared for the hoop itself, which should be 5 halves ml squared. So that should cover us for 3b. Moving on. 3c. The hoop rod system is initially at rest, held in place, but free to rotate. A constant force F is exerted tangent to the hoop. Find an expression for the angular speed, omega. All right, well, we'll use Newton's second law for rotation. Net torque equals moment of inertia times angular acceleration. Our torque is going to be our force times L, the radius at which it's applied. So there's our torque. Moment of inertia we just found was 5 halves ml squared. And alpha is just going to be omega final, which we call omega, minus omega initial divided by time. Where omega initial, it works out kind of nicely, is 0. It starts at rest. Therefore, we can rearrange this a little bit, knowing that omega naught equals 0, to state that our force is going to be, let's see, we'll have 5 halves ml times omega over t, or force times time equals 5 halves ml omega. We're solving for omega. 2f, I guess they use delta t instead of t. We'll write it that way. Delta t over 5 ml. So there's 3c. Okay, here we have it on a ramp, 3D. On the figure, draw and label the forces that act on the system. Each force must be represented by a distinct arrow starting at and pointing away from the point at which the force is exerted on the system. So draw it like you normally would. And justify your choice for the direction of each of the forces drawn in part D1. All right, I'll do that as I draw the forces. First off, probably the easy one always is the force of gravity, or weight. I'm just going to label that Fg. We also have the normal, and it's straight down, justify the direction. It's toward the center of the Earth, from the center of mass. All right, for our next one, we're going to have the normal force, the force of this surface back on our hoopty thing. So that's going to be at the point of contact, perpendicular to the surface, and pointing as if it were going through the center of mass. So there's our normal force. Finally, we have a frictional force. This one's a little trickier to come up with the direction of, but I'd say this one, first off, it starts at the point of contact, and this one's going to be going up the ramp. Our frictional force is at the point of contact of the ramp, and it causes a net torque to slow the rotation of the hoop. In order for that to happen, it has to be pointing up the ramp. So I think that would cover you for your 3 forces in part D. Let's see if we can derive an expression for the change in height of the center of the hoop from the moment it reaches the bottom of the ramp till it reaches its maximum height. That, to me, kind of screams conservation of energy. So we'll start with energy initial equals energy final. The initial energy is going to be its translational kinetic energy plus its rotational kinetic energy. And at its highest point, it's not rotating, so that's got to be equal to its gravitational potential energy. All right, its translational kinetic energy is 1/2 times the total mass, let's write that m total, times its linear velocity squared. Rotational kinetic energy is 1/2 its moment of inertia times its angular velocity squared, must equal gravitational potential energy mgh. And it's h that we're solving for. Breaking that down a little further, we have 1/2. Our total mass is going to be 4 capital M's times v squared plus 1/2. Our moment of inertia, we already determined, I total was 5/2 capital ML squared, and it says you could leave it in terms of I total. So you could just put I total in there and not substitute this in, but I think this looks a little slicker when we're all done. Omega squared equals m total. Oh, m total again is 4 capital M, 4m gh. Now v is equal to omega L. So knowing v equals omega L, we can go a little bit further, and this becomes 2 capital M omega squared L squared plus 5/4 capital ML squared omega squared equals 4 capital M gh. Now it becomes a bit of an exercise in algebra. I'm going to multiply everything by 4 to get rid of that 5/4. So I would have 8m omega squared capital L squared plus 5 capital M L squared omega squared equals 16 capital M gh. We've got 8 of these plus 5 of those. That's going to be 13. Therefore, h equals 13 omega squared L squared over 16g. 13 omega squared L squared over 16g is what I came up with for that. So I think that covers you for the mechanics exam. Thanks so much for your time, everybody. Make it a great day.